Welcome to the Explainer. An excavator tearing through solid earth isn't just a display of brute force, it's actually a total masterclass in fluid dynamics. Today, we're demystifying the brilliant engineering of hydraulic power, the literal driving force behind the heaviest machinery on Earth. Let's get into it.
Okay, let's dive into this. Have you ever wondered how exactly a millimeter of movement on a tiny plastic joystick instantly translates into lifting a 50-ton excavator arm? It's mind-blowing, right? Well, it all comes down to a flawless application of physics that turns a tiny, effortless input into massive mechanical output. The secret here lies in the invisible math, specifically Pascal's law. This is the absolute fundamental physics trick that makes hydraulics possible. Because an incompressible fluid, like oil, literally can't be squished, applying pressure transmits that energy equally in all directions. The fluid basically acts like a solid, flexible rod. It beautifully multiplies tiny input forces into absolutely massive output forces.
And because of that incredible mechanical advantage, this technology is everywhere. We're talking systems often running at staggering pressures of over 5,000 psi. In construction, it's powering excavators and heavy cranes. Up in the sky, it runs critical aerospace flight control systems. It drives high-force production presses in manufacturing, highly reliable braking systems in your car, and massive material handling equipment in logistics. It is, quite literally, the invisible muscle of the modern world.
So, our mechanical blueprint today breaks down like this. 1. The power of hydraulics. 2. Anatomy of the system. 3. The heart, which is our pumps and motors. 4. The muscle, our cylinders and actuators. And 5. The brain, the valves and piping. Let's dissect the anatomy of this machine.
Starting with Part 1, the power of hydraulics. Incompressible fluids transmitting energy. And this brilliantly illustrates the core concept. Because we use incompressible liquids, typically oil, we can build highly compact systems with an unbelievable power-to-weight ratio. A relatively small block of machinery generates massive power, all while maintaining smooth, precise, and completely vibration-free operation.
Moving on to Part 2, Anatomy of the System, the blueprint of hydraulic power.
To really grasp how this mechanical organism functions, we can just track the journey of a single drop of oil through 4 vital steps. First, the reservoir safely stores our fluid. Second, the pump draws that fluid out and creates flow through the system. Third, the control valves determine the exact path that pressurized fluid will take. And fourth, the actuators, which act as the physical muscles, receive that fluid and do the actual work. It's a brilliant, unbroken cycle that constantly transfers power.
Section 3, the heart, pumps and motors, generating flow, not pressure.
Notice the massive prime mover here, an electric motor. This is the core energy source that gets our heart pumping. It takes raw mechanical rotation and turns it directly into hydraulic flow. And here is a critical misconception you hear all the time. Pumps do not create pressure, they create flow. The pressure is actually a result of resistance to that flow downstream.
Now, engineers don't just use the same heart for every machine. There are strict engineering trade-offs. Gear pumps, they're simple, robust, and great if you're dealing with dirty fluid. Vane pumps operate nice and quietly, perfect for noise-sensitive environments. And then you have piston pumps, providing variable displacement and extreme high pressure for really demanding, peak-efficiency applications.
You can clearly see the visual contrast here. You've got a rugged, highly economical gear pump with fixed displacement on one side and an advanced high-pressure piston pump on the other. You instantly see the massive jump in structural sophistication required when an application demands variable flow control and absolute peak hydraulic efficiency.
Let's move to Part 4 and see how this builds. The muscle, cylinders and actuators, converting flow back to force.
So now we have to convert that flow back into physical force. The math is beautifully simple. Force equals pressure multiplied by area. But this dictates the fundamental trade-off of all hydraulics. To generate massive force, you use a cylinder with a larger piston area. But because it takes way more fluid to fill that larger space, the piston moves slower. So you gain incredible strength, but you absolutely sacrifice speed.
When it comes to linear movement, we essentially have 2 main types of mechanical muscles. Single-acting cylinders only have one port. They're powered in one direction, and they rely entirely on gravity or a spring to push them back to the start. Double-acting cylinders, on the other hand, have 2 ports. Hydraulic fluid can power both the extension and the retraction.
To put that into perspective, in a single acting cylinder, pressurized fluid enters through that single port right at the bottom. It pushes the internal rod up, but when the pressure drops, the weight of the load, or a heavy spring, just pushes the oil back out. It's inexpensive, super reliable, and absolutely ideal for basic lifting. In contrast, a double-acting cylinder utilizes two separate ports. Fluid pumped into one side forcefully pushes the rod out, and fluid pumped into the other forcefully pulls it back in. This grants the engineer versatile, extremely precise, bi-directional control. It gives you the muscle to power both the push and the pull.
Finally, Part 5, the brain, valves and piping, directing and connecting the system.
You see, muscles are completely useless without a nervous system to tell them what to do. Control valves act as those critical gatekeepers, determining the exact path, the pressure limit, and the flow rate. Every single time an operator moves a joystick, they are shifting internal spools inside valves exactly like these to instantly route that pressurized oil.
And that directed oil travels through the physical veins of our system, the pipes and hoses. But listen, this isn't basic plumbing. Pressure drop inside these lines is the absolute enemy of efficiency. Longer pipes, smaller diameters, sharp ends, or higher fluid viscosity, they all create massive resistance. A badly sized hose will quite literally kill the power of the entire machine.
So the crucial point is, to maintain all this incredible power, we rely on an unsung hero, the multi-purpose reservoir. It doesn't just hold the oil like a bucket. It's a brilliant, multitasking organ. It actively dissipates heat, allows heavy contaminants to safely settle out, and lets trapped air bubbles escape. It is deliberately sized 2 to 3 times the pump's flow rate, giving the oil enough time to physically recover before making that violent journey all over again.
It is just a beautifully interconnected system. Next time you smoothly ride an elevator, confidently hit your car brakes, or see a massive tractor working out in a field, take a second to consider just how much of our modern civilization is secretly powered by incompressible fluids silently transferring energy. It's everywhere. Thank you so much for joining me on this explainer. I really hope it gave you a brand new lens to view the world. Keep learning, and I'll catch you next time.